Welcome everyone back to Unit 4 now. We're in the application section of the course. We've studied the topic of derivatives, how to find them, all the differentiation rules, and now it's time to apply that learning to actual contextual situations. So in a nutshell, we'll be looking at various real-life situations in this unit and applying the concept of derivatives and rates of change and studying that in a good amount of detail the next couple of days here. So we actually have 2 units to finish the semester off. One is called contextual applications, where we actually use and study ways to use rates of change and derivatives in more like real life situations. And then the unit which is called the analytical applications, which is really back to the roots of calculus, and we just really are studying the graphs of curves and things and using the derivative as a tool to do that. Well, the objective in this next couple of days here is to apply rates of change in context, like basically in a word problem or story problem. And so we're going to go back and revisit something we looked at very early in the course, average rate of change and instantaneous rate of change today, in light of what we've learned recently about finding derivatives and computing derivatives. And as we go the next couple of days here, we'll apply them in various contexts. A very common one is a problem about motion in one direction or one dimension, and studying the relationship between position, velocity, accelerations, and such as that, describing a moving object and using calculus as the tool to do it. Let's go back and look at the topic average rate of change versus instantaneous rate of change. And I asked the class today, which one of these, if I were looking at a graph of a function, and the 2 quantities we wanted to measure were the average rate of change of the function. I'm going to put here average rate of change of f of x on the interval a to b. And the other quantity to be measured here is the instantaneous rate of change of f of x at x equals c. I asked them which one of these can be represented with a tangent line and which one can be represented with a secant line, or a line containing 2 points. And we remembered that it's the second one that is the slope of a tangent line, and the average rate of change was the slope of a secant line. What gives it away to me is that the word instantaneous means we're studying something at a specific moment or instant in time, and my visual of that is a tangent line that touches the graph at one point, versus average rate of change is done over an interval where there would be 2 points, a starting point and an ending point. Let's actually start with that one then. The average rate of change, I'm going to abbreviate it AROC, exhibited on a graph of the function would be the slope of a secant line. Between 2 points. So let's, on my graph, pick 2 points. Let's maybe even assume that A is just, I'm going to mark some random point out here and call it A. And I'm going to mark a different random point out here and call it B. And on the graph, I can find, or at least estimate, f of A and f of B. And now the average rate of change is basically describing the change in the function values compared to the change in the input values. So a starting context for this might be, maybe the function that I'm drawing a graph of represents, remember the very first day of class and we were watching the roller coaster? Maybe this is the graph that shows how many feet or how many meters the coaster has traveled over a particular interval of time. And so these 2 function values would be measured in meters or feet, and these 2 x coordinates would be measured in seconds. And so if I actually take a time and draw a line connecting these 2 points, and I'm going to draw right here. Okay, so remember that the rise and the run are measured in the units of the axes. Okay, so to find the rise and the run, I would simply use my slope formula. This would be y2 minus y1. So that in this context, that would be f of b minus f of a over b minus a. The units of this answer, let's say this whole thing turned out a number like 7. Then the units would be found because I know that the function values are measured in whatever it is measured in. Let's take the roller coaster problem. Maybe this is measuring meters. And maybe this is the time scale, which is measuring seconds. Then if I want to know the unit of this answer, let's say this whole calculation spit out a number like 7, then the units would be the units of f of x, which is meters, divided by the units of the x, which is seconds. So in a minute, we'll examine an example of that. Now, at an instantaneous point, we can mark another number. So I'm going to put C arbitrarily somewhere in here. Let's say C is here. Now that is just a single instant in time. So let's put a dot there. I can find f of C. But what I really want to know is the slope of the tangent line. If I draw a tangent line to this point, actually let's just use the line tool and do it right. So let's draw that again here. And I'm going to attempt to draw a tangent line to this point. And so really, if we learned anything from the first unit of studying derivatives, the main application was it's to find the slope of a tangent line. So the instantaneous rate of change at x equals c, that's kind of the verbiage of what we're doing. But in the graphical form, that is the slope of the tangent line at the specific instant x equals c. And what we learned in the first unit was that that slope can be calculated with the function's derivative evaluated at that c. So again, if this graph was measuring the distance that the roller coaster went over a particular interval of time, then the slope of this tangent line is the rate of change of the coaster at that instant in time. And because slope is still rise over run, and it would still be meters over seconds, the unit of this answer would also be meters per second. Because whether it's a tangent line or a secant line, there is still a rise and there's still a run. And the rise would be measured in the units of the y-axis, and the run is measured in the units of the x-axis. Well, let's just practice applying those two definitions first. So with the warm-up problem, there really is no context. It is just to practice those two calculations. So we want to find the average rate of change of this function, and we'll use that formula. So the a is 0 and the b is 5. Of course, I encourage you to pause the video right now and try and work this out yourself. Calculators are, of course, permitted. If you want to keep watching, I'm going to work it out as well. So to find f of 5, we will plug 5 into the function. And that would be 5 cubed plus 3 times 5. And that's going to be 140. F of 0 would very easily be 0. And we're dividing this by 5. So if I take the calculation 140 divided by 5, we get the answer 28. And there were no units mentioned in this problem. This is just to practice the formula, so this is just a number at this point, 28. But now we want, in part B, the instantaneous rate of change of f at exactly 3. So this calculation is going to be f prime of 3. So maybe at the top, I'll also just work out this function's derivative. And of course, we know our differentiation rules now. So that derivative is 3x squared plus 3, which means my f prime of 3 is going to be 3 times 3 squared plus 3. So that is also going to be 30. Well, let's apply this to an actual context now. So I'm going to introduce another function to you. And in the paragraph up here, we're going to describe what this equation does. So here's the context. It says at midnight, midnight will be represented by the time t equals 0. A large tank begins to be filled with water. The number of gallons of water in the tank at time t, which is measured in minutes, after midnight is given by this equation. W of t is 4/3 t to the 3/2 plus 4 square root t. And there are two parts to this problem. One's on this page, and the next page is going to be part B, which is going to ask you the instantaneous rate of change. A says find the average rate in gallons per minute that water enters the tank from 12:15 to 12:30. Let's think about this graphically once more. There's a function W of t. So that's going to be the name of the y scale. And we're told that that measures the number of gallons. Okay, so the unit of this scale is gallons. The other scale is going to be the time. The independent variable is time, t, and it is told to be measured in minutes. Not just minutes, but minutes since midnight. So now, if you read the question carefully, we're finding the average rate, in other words, the average rate of change of the water that enters the tank from 12:15 to 12:30. Now we have to read the context clues again to see, okay, what really on the t-axis, what numbers are we actually going to use? Remember, t equals 0 represented the time midnight. Okay, so think about this, 12:15 a.m., that really means 15 minutes after midnight, and 12:30 a.m. really means 30 minutes after midnight. So in this context, the time interval really is the numbers 15 to 30. Okay, or that could be expressed as an interval notation, 15:30. So we are finding the average rate of change. And so this will be W of 30 minus W of 15 divided by 30 minus 15. So now here's where I would encourage you to use your calculator, because the numbers aren't going to come out super nice here. And then do this math. So we're going to take this and divide by 15. And excuse me, I'm going to bring up my calculator that already has this equation on it. Okay, so I've gone ahead and entered the function here already. 4/3 x to the 3/2 plus 4 root x. Remember, on your calculator, you have to use the variable x, not t. So now I'm going to go back to my home screen and figure out the average rate of change. The simplest way is to go and use your alpha key with the trace key and bring up the list of equation labels, and we're using y1. So just like entering in function notation, we want y1 of 30 minus, and then alpha trace y1 of 15. So this will just give us the difference of those. That's going to be the rise in our slope. I got 148.046. I'm going to write down at least the first 3 decimal places of this. Peek at that again, 48.046. And I've got to still divide that by 15. And I've got the final answer, 9.869755. College Board rules for rounding in AP Calculus is to round to 3 digits. So we are going to call this 9.870. 9.870. Now, we were told a unit in this question, but typically you would not be told that. You might be asked to provide the units on the answer. So if we were, simply know that this is the slope between 2 points. Somewhere there is W of 15, and somewhere else there's W of 30. What the graph looks like in between, we really don't know without graphing it. But we just found the slope between those 2 points. And so the rise, this 148 is measuring gallons, and the time is measuring minutes. So my unit for this whole rate is gallons per minute. Because if you go back one step, this side tells us that during this 15 minutes, the tank gained roughly 148 gallons in 15 minutes. And so by dividing this, we're finding the average number of gallons per minute during those 15 minutes. Okay, well, part 2 of this is to find an instantaneous rate of change. So same introduction, same function, but this time it says find the instantaneous rate of change, also going to be in gallons per minute, that is entering the tank at the moment that the tank contains 48 gallons. So there's an extra little wrinkle to this one because, again, think of the graph. Okay, and my graph is modeling gallons here and time here. It says find the instantaneous rate of change, or find the instantaneous rate at which the water goes into the tank at the moment that the tank contains 48 gallons. Well, I know this is instantaneous. I'm going to have to find a derivative, and there's going to be some number c. My problem is I don't know the c. We were told to use the instant that there were 48 gallons. That's actually a number on the y scale. So that leads me to think I've got to figure out at what instant was the volume of water 48 gallons. And so that leads me to think I've got to solve and figure out when does this water calculating function measure 48. So to find the c, I've got to solve when does the water actually equal 48. Now, that looks like it should be an algebra problem, right? It looks like I should be solving 4/3 t to the 3/2 plus 4 root t and setting that equal to 48. And that really is what we will be doing. However, that does not look like one we're going to solve with algebra skills at all. Nobody is going to want to do that. So my suggestion to you this time is, this is another kind of an AP Calculus exam tip, is you're going to be given the opportunity to solve this equation just by using your calculator. So I'm going to pull up the calculator. I've already typed in my W of t, which is y1. Now I'm going to graph the 48. So y2 is going to be 48, and I'm going to graph now. So the blue curve is the water function W of t. And of course, it starts at 0 and it just increases. But now here's 48. So what I want to know is this one right here. I want to know this point and what the t value is. Okay, so if you don't have your graphing calculator with you, I encourage you to pause the video and grab it and make your graph look just like mine. And I'm going to describe how I made it look like this. I made sure that when I hit the window button, I made sure that the y maximum was over 48. So I just picked 60. Okay, I made the scale count by tens just so I could see some tick marks. My x scale, I wasn't really sure how far I'd have to go, so I made the x max 50, and I just hoped that would be far enough. And the scale really does not matter too much. If you want to see more tick marks, you can count by 5s or 10s just so you can see some tick marks. Now here's my graph. So notice that this scale is counting by 10s and this scale is counting by 5s. So just estimating it, it looks like it's between 5 and 10 minutes, but I'm not for sure. So now Again, if you want to pause the video and grab your calculator and set it up like this first, I'm going to go ahead and finish the problem by solving for this spot right there. This time you want to use your second button and then the trace button. That's the calc menu up here. Option number 5 is the intersect tool. So go ahead and just type in 5. Now, you need to use your cursor keys and move the cursor as close to this point as you can. Now, it already tells me where the cursor is, which is off the screen at the x coordinate 20. Right now, this is about 8 or 10 or so, so I'm going to use the left arrow to bring the cursor back onto the screen. It should be appearing shortly. Okay, so you get it as close as you can. It looks like I'm almost to 9. And essentially now it's going to ask you where on the first curve to guess, and just basically hit enter. It's going to ask you where on the second curve to put the guess, and I'm just going to leave it at the same spot. Essentially, you just enter 3 times. Now enter another guess. And the third time around, it gives you the intersection point. It says the x was exactly 9. So I can go and record that as my number. Now that means that since it's exactly 9, we may have just could have guessed and checked until we found it, but this using the calculator was right a lot faster. So now I know the answer to this question is going to be w prime of 9. Now notice we still have to work out this thing's derivative, so maybe we should do that on the side here too with our differentiation rules. Good time to practice that. So the first term, I'll keep the 4/3, and then I'll use the power rule. So bring 3/2 down. 3/2 is going to decrease to 1/2. And then with this other term, if you memorize that the square root function's derivative is 1 over 2 root x, this is going to be 1 over 2 root t. Simplify your coefficients a little bit. So this is going to be 2t to the 1/2. And over here, this 4 cancels this 2. So it's going to be 2 over square root t. So my final calculation is going to be 2 times 9 to the 1/2 plus 4 over square root 9. And 9 to the 1/2 is the square root. So this is going to be 2 times 3 plus 2 over 3, which makes this final answer 6 2/3. But now my unit is going to be in gallons per minute simply because this is still the slope of the function w, whose one scale is measuring gallons and the other scale is measuring minutes. So this automatically is in gallons per minute. Okay? So even if I didn't tell you the unit was gallons per minute, you would be expected to know that it was going to be gallons per minute. Well, this will be all for today. I'm going to encourage you to start working on the assignment sheet in this unit and maybe the first couple of problems, and then we'll pick up with more next time. We'll see you back here soon.